Now, we've all heard and used this property where root x times root x gives you x, right? So just simply multiplying the roots of the same indexes and radicands will get rid of that root. The thing is, when you do more complex roots, like cubic roots, and when you're trying to rationalize quartic roots, you have to understand why this is the case. Remember that there's a couple of hidden numbers here. The indexes here, when they're not listed, are really indexes of 2. And the exponents underneath the root here, when they're not listed, they're really indexes of 1. Now, why is that significant? Because, remember, according to the exponent law, that when you have two bases that are the same and you multiply them, their exponents are added. And so that means that x1 times x1 gives you x to the 2. Well, that's the same thing, even if they're under the root. That wouldn't change. So if I go x to the 1, root x to the 1, multiplied by root x to the 1, that is going to give me, if I keep the root momentarily, that's going to give me x to the 2. Now, when this happens, remember that in math, if you can simplify, you should. And so this actually breaks into x times x. And since this is a root or a radical with an index of 2, then anything that occurs twice under the root is going to be moved as a coefficient, which would be these pair of x's here. Now, when we do that, well, there's nothing left under the root, right? It's just x. So that is how, when you go root x times x, it eventually leads to x, because we know that once I get those exponents added, and this becomes a 2 under the root, and I simplify that root, then I'm left with only x. Now, the same is true when we have cubic roots. So let's say I go cubic root x. And my goal is to get it into a position just like this over here, where when I simplify the root, it's going to be everything out of the root. So there will be no more radical left. So x. If I go root x times root x, let me just rewrite that here. Right now, that is going to be x1 times x1. That is just going to equal cube root x2, which when I simplify, that will not simplify into a number that is no longer radical, right? Because you can't pull out groups of 2 when the index is 3. So in order to simplify this here, and if I cross this one out, if I wanted to get my cube root x into a position where when we simplify it, you remove the root, then I'm going to have to multiply it by cube root x twice. And I just should have put a cube root here. It was an accidental leave, so it should always be cube root. So cube root x times cube root x times cube root x. And when I do that, remember that they have invisible exponents here, that when these are added up, x to the 1 times x to the 1 times x to the 1, what you end up getting is cube root x to the 3. And when I simplify this and I rewrite this, it's really x times x, which, since the index is 3, any groups of 3's will be removed here. And that would just leave you x with nothing else under the root. So here, when it comes to cube root x, we say that instead of just like the squared or the root x here, where root x times root x gives you x, we say that cube root x times cube root x times cube root x, so it happens twice, that leaves you with x. Lastly, if I have, let's say, quartic root x, so quadra root x here, and again, I want to get it into a position where when I simplify it, that it will no longer be a radical and it'll just be x. Well, remember that this has an invisible 1. So if I go multiply by quartic root x, right now that brings me to x to the 2. Then if I go again, multiplied by quartic root x, these three added together will bring me to x to the 3, which won't simplify to just x yet. Then I do one more here, quartic root x to the 1. And then now if I add these, I now have quartic root x to the 4. And then now these 4s, they will simplify because, again, same idea. If I go like this and I go x times x times x times x, I can then, since the index is 4, I'm looking for groups of 4. So this whole thing will be pulled out, and then I'm just left with x. Now, this is really important because when we want to simplify or rationalize the denominator so that it's no longer a radical, we have to multiply that radical and the radicand to the appropriate index to remove that root. So for example, if I have 1 over root x, well, this is disliked in math because it's an irrational number, right? We want to remove any radicals from the denominator. Well, since this is just a root x, right, and in an index of 2, all I have to do is just multiply this by root x, and those roots are going to cancel because it simplifies to x. Now, what I do at the bottom, I also have to do at the top. So I would just multiply the top by root x. And then that's going to give me, remember that root x times root x gives you x. And then 1 times root x, that's going to give me root x over x. And this is fully simplified. Now, when I have cubic roots, so 1 over root cube root x, let's say. Okay, well, now that this is a cube root x, and this is an invisible 1, in order to get the cube root x to just x, I'm going to have to multiply cube root x twice so that the exponents add up, like this. And so this bottom here is going to equal to just x, which is perfect. I got rid of the roots, which is what I want. But what you do at the bottom, you have to also do to the top. So we're going to take this here, and we're going to go multiplied by cube root x multiplied by cube root x. And when we do that here, well, this is what we're left with. 1 times cube root x times cube root x. That's going to leave you with cube root x squared, which can't be simplified any further. And that's going to just be over x. And since there's no radical in the denominator, this is considered fully simplified.